Good. So what's going to happen now is that now we finished talking about a function field. Like what we care about is a function field extension. Okay, this is like in Galois. You don't care about a field, you care about a field extension. Here it's more complicated. Here the function field is a field extension by itself, for instance, degree 1, blah, blah. But we really care about function field extensions because that's how we are going to construct function fields. We are going to start with k of x over k, and then we are going to look at a larger function field, maybe kxy, like kind of a slang, but I don't know, minus something like this, or stuff, whatever. So the way we will understand general function fields is by extending them from known function fields that we understand already. So most of the theory is actually about function field extensions. What we did was like the basic, like looking at one function field, understanding the points, the OP, MP, places, valuations, and then we understood like the genus of the function field, and then at some point we understood also to some extent differentials and others, and then we had the Riemann-Roch theorem. So we kind of completely understand our function field. Like we don't understand it. We just know what are the parameters that are important and so forth. But given a function field like that, even if I don't know if you know if it's a function field or whatever, technically it's not written in a. You need to take the fraction field of this ring or something, but whatever. So given those, you don't know what the genus is. I mean, you don't know. You have no tools at this point to compute anything about it. You just know this one. And the way we'll do things is that we'll understand, given a function field that we understand, and understanding usually the Galois group corresponding to the extension, we can understand this function. That's the fun part of the course. Now, no more definitions, like you'll see. Generally speaking, no more like heavy definitions, except for like one or two, but all of them are really reasonable and understandable, and mostly are like working algebraically, which is fun. I think it's nicer. The problem is that this takes like maybe 3 or 4 times like what we invested so far in terms of time. That's how it is. So most of it will be in the videos, not in the actual course. And I'm only taking parts that are like the balance is awful, like 3-hour proof for a statement that you can just understand. Right. So what I'm going to do is increasingly talk conceptually and describe the definitions and hide some of the proofs. But all of the proofs are in the notes, and I will also record them. So if you want to see, I'm not hiding anything, but I just can't do it in the lectures. It's too much. I did it last time, by the way, all of it in slides. It was horrible. My best of students said, honestly, I mean, it wasn't pleasant. So I'm not going to do that. We're going to do it the right way. You just need 2 courses, and that's what actually going to happen now. The problem is that some of the definitions, like in the genus, they require a proof. You can't define something if something is not like well defined. So I can't just do that, as I say. I have to. It's like it's my work, not yours, but it's not so easy to do. So I'll try my best. So what will happen now is we're going to just do the baby steps, defining what is a function field extension. Next time we are going to do all the basics. It's very easy, and start doing examples. Now you can't do examples yet. You don't have enough knowledge. That's why we need like many lectures to do. But I will give you one. First of all, I will do one example in which I kind of cheat my way through it, and we can do it. It's fun, but you'll see it's really restrictive. I can't do it in general. So what I'll do, I'll give you a theorem. It's called Kummer's theorem. It talks about very simple Galois field extensions, cyclic extensions, with some asterisks. And I'm just going to give you the theorem. You are not entitled to use it. Like you see, you need to spend 15 hours building the theory. But I'm going to give it to you. Like you have to return it back. You can't use it. But using this theorem, we're just going to play with function fields and understand them. And after doing that, we are going to start like the formal treatment of like the more heavy lifting. Most of it will be in videos. So again, we are going to do the basics now and do an example. It's like a 1.5 hour example. It's long. We do many things just to understand everything. I think it will. It's going to be insightful. And then we are going to see less and less proofs. Okay, at least the heavy proofs. because some of them takes hours on hours. I mean, I would see them if I were you, because it's really interesting. But I'm not going to assume you saw them, yeah, and so forth. Okay, so you can choose. You can like all you can eat. Like, do what you want. Okay, questions so far? Also, next week I'm here, but next week, which incidentally is the time that we start to do the heavy lifting, there is a Weizmann, at Weizmann there is a winter school. I don't know if you heard about it, but you should go there. It's nice. And I'm talking there, so I have to go there. It's like 4 days or something. I'm not going to be here. It's like at the same time. So I'm going to record also these videos. Like I'm going to record, apart from recording the extra proofs, I'm going to record the lecture, which won't contain the extra proofs. It will be very clear what's an extra proof and what's not. Okay. But that's next time. Next week we are meeting. Okay, so the title, that's unit 16, function field extensions. That's where the fun really starts. And the fundamental equality. We won't get to the fundamental equality today, but that's the name. We're just going to define essentially what is a function field extension. So here's the definition. So let's say you have now 2 function fields. So let's say you have f. Usually we wrote f over k so far. For some reason, I'm not sure why, we are going to write it as f over L and E over K. Be function fields. I don't know why we split it K from L, or started with L from the beginning. I mean, I'm following notes and books, so everyone do that. It's really hard to not do it anymore. So you have these 2 function fields sitting there, like maybe this is k of x over k, and this is maybe one of these things. I don't know what it is. 2 function fields. We say that f over L is an extension. It's not a field extension, it's a function field extension. Right? Every function field by itself is a field extension. Is an extension as a function field of E over K if 3 things hold. 2 of them are obvious. The 4th is kind of, I need some talk about. So I think of this as the larger one, like more functions. So first of all, and again, these are functions, these are constant. These are functions, these are constant in my mind. So first of all, I want E to be a subset of F. I want to have more functions here, or at least the same compared to here. And also the same for the constants. I don't want it to decrease constants. So this is the smaller function field, so less constants here maybe compared to that. That makes sense, I think. But the one thing is that I don't want that, I mean, these are constants. So I don't want them to be functions here. I want them to be constants here. So L intersect E equals K. Namely, everything that this function field thought of as a constant, if it is in the smaller function field, it's also a constant there. Right? It makes sense. You don't want, I mean, these 2 are functions and these are constants. So, okay, this is bigger than that, but not that bigger. Like a constant is not a function, it's a constant. So if this is the way of writing that. If you take an element that is in L, it already appears in E, it's actually in K. It's a constant. So let's do a picture.
Usually, I say the simplicity is the same, the addition is the same.
Yeah. It's a right. It's not a subset. It's field extension. Right. Sorry, that's what I mean. Right. So the picture you should have in mind is maybe something like that. Maybe tilted a little bit. E over K is a function field. F over L is a function field. But you see, L doesn't go to the height of E. It's like smaller. It's close to K. And then you have these. So E is a subset of F. So these are inclusions. I mean, E is a subset of F, K is a subset of L. Of course, L is a subset of, these are the constants in F, these are the constants in E. But also you have this relation, which does not appear in the picture, but everything here that is here is already here. Constants can never be elevated to functions. Right, so the picture you should have in mind is that you kind of understand this function field. You understand the prime divisor and the genus and everything you want to understand about it. And now you want to understand this function field. So for example, you want to take a prime divisor here and ask what are the prime divisors that are kind of in a sense related to it. So I'm going to do it like that. That's the first thing that we'll do. And again, we'll start slowly today. It's really, from this point on, I think the course is extremely nice. That two last lectures were a bit kind of, I don't know, mysterious. So let's do it in this direction. So let's start from a prime divisor here. You have prime divisors here. Now the problem is that I can't use P for everything. So I'm going to use like a weird capital P that looks like a big beta for prime divisors here, okay? So let's say you have like this, I don't know. You can look at the notes, it's weird, it's like a calligraphic something. Be a prime divisor. It is always easier to go down, so because you have more information. So let's take a prime, actually not as in this picture. Let's take a prime divisor here. And what I'm going to do is to associate with that prime divisor another prime divisor here, a unique one. So from this, I'm going to get some prime divisor here in a second. Right, so what is a prime divisor? So it could have been a valuation or a place or a valuation ring or what have you. And we actually slightly talked about those things when we talked about them, about field extensions before function fields. But so let's consider the place. I mean, you can write it in many ways, but let's consider the place that corresponds to this beta or capital P. Right, so this is as a function. I mean, what is this? So this is a function from F to some. Don't worry about that too much, but the residue field union infinity. Right, that's what it is. Right, everything OB goes to something, and outside of OB it goes to infinity. But right, so this is a function from F. So if you want to find a prime divisor that comes from this beta and it's related to E, so what should you do to this function? Right, so how can you get from this maybe a place of E? Sorry? Exactly. So very good. So let's look at this thing. You can actually start from anything, but start from a place it's easy because set theoretically it's kind of obvious what you want to do. You want to find a place of E that is related to that, just restrict it to E. So let's consider this thing. Now, there is a slight technicality. This is not necessarily, I mean, this thing is a good candidate, but this thing is not necessarily a place of E over K. I mean, there were little letters in the contract, and the little letter said that a place has to be trivial on K and non-trivial on E. Right, that was these things. And well, this function is going to be trivial on K, because trivial on L, right, exactly. No worries about that. But potentially it could be trivial on E, accidentally. Because it's not trivial on F, it sends something to infinity, but maybe everything in E doesn't go to infinity. That can happen, actually. So assume that it doesn't happen. We are going to give conditions. Once F over E is a finite extension or even algebraic extension, this never happens. So don't worry about that. But for now, just assume that is not the case. So assume, this is under this assumption, that phi of B, phi B, when you restrict it to E, or just generally, is non-trivial on E. Namely, one of the elements in E goes to infinity. But that's assumption. But that's an okay assumption. It will follow from, it will hold in everything that we will do. because our extensions will be finite, in particular algebraic. And we're going to prove that and everything, so don't worry. So, good. So what we are going to, just for now, let's denote. So denote the prime divisor corresponding to this restricted place, assuming it's a place, by little p, like as usual. So this is B, this is P, just a name, so that we have a place, I want to give it a name of a prime divisor. Let's call it P, like the good old P's. And the notation is that we say that, the slang is that capital P lies over little p.
P is the divisor of the place.
Right, P is the prime divisor corresponding to this place. Assuming it is a place, assuming it's not trigonometric. Right, right, because a prime divisor was kind of an abstract notion. Technically it was the equivalence class of places and so forth. So, but okay, if this is a place, it has an equivalent class, then P is the prime divisor that corresponds to the equivalent class of this place.
Usually we know P is places and as the place of divisors, and now it's divisor. I don't know.
No, prime divisor are denoted by P all the time. Oh, yeah. No, the course is hard enough. I'm not going to. Yeah. Right, so we say that P lies over P, like capital P lies over small p, or the other way around, or little p lies under. So I'm going to use those words in capital P. By the way, now we are kind of going to the regime of algebraic number theory, if you know, like prime decomposition and stuff like that. Now the arithmetic will. So if you know algebraic number theory, you saw this thing. A prime in Z may split in a larger integer into something else, to other primes and so forth. So that's really what's happening here. Good. And maybe we'll finish with this. So consider the valuation now. Let's move to valuations for a second. VB. Right, so you take the big prime divisor at the top, it has a place, good, but it also has a valuation. Right, so this is a valuation. It goes from F star to Z, if you remember, right? We proved that this ordered group is always Z. And we actually chose that to be the onto map, right? Actually, valuations come in also classes, and we chose VP to be the one that is onto Z. That's how we chose VB out of all of the evaluations. And so if you think about it for a second, VB, when you just restrict it to E, moving zeros, it's a subgroup of the entire group, Z, just a subgroup of Z. Right, because it's closed under, it's a field, so the image is a subgroup, it's closed. If you have two elements, then you can find the images that take the product. We use it all the time. So we know either this thing is zero, what are the subgroups of Z? Either this, or it's some number, right? Some integer larger than 1 times Z. Now, this cannot occur because under our assumption, at least, we know that P restricted to E is non-trivial. So there is a pole somewhere. So something has to go, there is some element here that goes to something which is non-zero. Someone has a pole by assumption, and we need to justify the assumption. But under this assumption, there is a function that has a pole at that particular point B, a function in E. And so that will be reflected by the valuation, it should be negative. So we really know that there is such an E. So and let's finish with that. The valuation V little p now of E over K is given by so what I'm saying is that, little p has a valuation, right? Because it's a valid place. It's like a prime divisor. But you can ask, what's the relation between the valuation of little p and the valuation of capital P? Then what I'm saying is that it's the same thing up to a normalization by this E number, right? Because this was chosen to be the one that's onto. And this has image E times Z. So to make it onto, you need to divide by E, by this number E. And this integer, let me just finish with that. The integer E is an important one. Sometimes you write it like that also, just to make sure that you understand which E you're talking about. If you have many prime divisors floating around, is called the ramification index. That we talked about? Yeah, exactly. But when we talked about it, we didn't have function fields, we only had fields. If you remember, we talked about it before we talked about function fields, really. So, but it's the same thing. Yeah, F and E, yeah, right. It coincides with that. It's the same definition. Right, so, but let's finish for today. I will talk about other parameters next time. Yeah, see you next time.